okay, on the expectation maximization algorithm. So in general, expectation maximization is a very powerful tool for maximizing likelihood. Okay, it doesn't go to the global maximum, but it's an iterative algorithm that's easy to implement. It usually results in a very intuitive algorithm. Okay, and that's what I'm going to show you. Okay. And the basic idea is, we're going to introduce what's called a hidden variable. Okay, and this or sometimes called a latent variable. And if you knew this latent variable, then it's easy to set all the parameters without any effort. Okay, and so what we do, just like with if we knew the centers of the K clustering, it's easy to figure out what's the optimal clustering. Okay, or if we knew the clusters, then it's easy to figure out the centers. Okay, so it's similar in this situation. If we knew which data points belong to each bump, okay, then we can compute the mean of the bump and the covariance matrix for the bump. Okay, and in some sense, the weight of the bump is just the fraction of data that belong to that bump. So if we knew that, we could easily compute all our parameters. Okay, and so what we're going to do is a similar algorithm which says, supposing we know that, okay, supposing we know that, then we can compute all the parameters, and then we'll use the parameters to estimate how much data is inside each bump, and then repeat. So that's the basic idea. Okay. So the basic idea is, if we know which data belong to bump, let's say J, then that easily will tell us what are Wj, mu J, and sigma J. Okay. And then if we know Wj, mu J, sigma J, okay, if we know all of those, then we can figure out which data belongs to bump J. Which data belongs to bump J. Okay, and so what we do is similar to the k-means algorithm. We alternate. We pretend like we know which data belongs to which bumps, and then optimize the bump parameters. Then we use the bump parameters to figure out, which data belongs to each bump. So just like in k-means, we pretend we know the clusters, we can get the centers. We know the centers, we can get the new clusters, and so on. Repeat. Okay, so that's the basic idea. Okay. Now, so let's describe the first step. The first step is we have to initialize, and one way to initialize is just using a K clustering. That gets us, initial data that belongs to each bump. Okay, so you could do K clustering. Okay, so random assignment of data to each bump. Okay, but initialize. So let me say initialize. Okay, so for example, using a K clustering. So that tells you what data belongs to each bump. Okay. So in general, okay, let us define gamma n j. Okay. So n is the data point xn, and j is the bump j. Okay. So I'm going to define gamma nj is equal to the part of data point xn, the part, okay, I'll put that in quotes, i.e. fraction of data point xn that belongs to bump j. Okay, so you might be thinking, what? Why do I need a part of the data point to belong to bump j? Doesn't the data point either belong or not? And that's true in a hard clustering. Okay, but the interesting thing about the density estimation and the Gaussian mixture model is, let's take, for example, this data point here. So let's take this data point here. We don't have to commit to the data point belonging exclusively to this bump. We can say, for example, that this data point half belongs to this bump and half to that bump, and basically 0 to this, 0 to that. Okay, so we're allowing fractional bump membership. Now, of course, when we do the initialization using clustering, that's going to assign each data point, exclusively to one bump or the other. So it's possible that gamma nj, okay, so think of gamma think of gamma as a matrix, sometimes called the clustering matrix. Okay, so gamma has the data points along this dimension, so this is n, and the clusters are on this dimension, so this is k, this is n. Okay, so this is xn, for example. A row corresponds to xn. Okay, and if it's all 0 everywhere except for one spot, which is 1, okay, then we see that data point belongs to exclusively to one cluster. But we're allowing these to be fractional. So what we require is that the sum in a row is 1, and they're all positive. So gamma nj is non-negative, and the sum over j of gamma nj is equal to 1. So a data point can belong to a part of a data point can belong to a cluster, okay, a bump, but at the end of the day, the entire data point must be allocated. Okay, so this is a generalization of the clustering problem, where in the clustering problem, we require that each data point belong exclusively to one and only one cluster. Okay, but now we're doing density estimation, so we can allow the chances that this data point was generated by that cluster to be some value, and the chances that this data point was generated by that cluster to be some other value. Okay, and so those chances kind of relate to what fraction of this data point belongs to this bump and what fraction belongs to that bump. Okay, all right. So now, okay, I'll keep this part here, but we don't need the explicit formula anymore. Well, although we do have it. Okay, so let's keep the formula. Okay. And now, let me show you the algorithm in action. So this bump membership matrix gamma is very crucial to the algorithm. Okay, and we have started by initializing using a K clustering. So that means we have initialized the bump memberships. So assume, step 1, assume you know the bump memberships gamma and j. So you know the bump memberships gamma and j. Then, okay, let's figure out, how much data belongs to each bump. Okay, so let's call that n sub j. How much data belongs to bump j? Well, that's just the sum over your data points of how much of that data point belongs to bump j. That's just gamma n j. So this is how much of data point n belongs to bump j, and we've added that across all data points. So you can think of it as the column in this matrix. Okay? So this column is bump j, okay, and how much of each data point belongs to bump j. I'm going to add that all up. Right? That tells me how many data points, okay, in terms of adding up the fractions of data points, how many data points belong to bump j. The total number of data points, n, is just equal to the sum over j of nj, and that comes, if you sum this over j, you'll find that it equals, n, okay, because of this condition that the sum of the rows are 1. So if you sum over j of nj, basically you're summing every entry in this matrix, okay, which is the sum of n rows, and each row sums to 1, so you get n. Okay, that's good. Okay. Now, the volume, the amount of data that belongs to bump j is the weight of bump j. So wj is just equal to nj divided by n. Very easy update. Okay. And let's see, what about the center? Well, we said that, assuming that all the data that belongs to the bump, was generated by the Gaussian for that bump, well, then the average data point that belongs to that bump is exactly the center. So mu j is equal to the sum, okay, over all data that belongs to that bump of the data point xn times the fraction of it that belongs to the bump. So the sum from n equals 1 to big N. So this is the fraction of data point n that belongs to bump j. Okay, so I'm adding up the data points that belong to bump j, weighted by their fraction. Okay, but now I need to take the average, so I divide by the number of data points that belong to bump j. Okay, and I can get the shape parameter, sigma j, okay, is the average of the outer products, so it's equal to, sigma sub j is the average of the outer product. So it's 1 over n sub j, the sum over all data points, okay, the fraction of the data point that belongs to the bump, okay, times the outer product xn transpose. Okay. So sigma sub j, sigma is the average outer product minus the mean outer product. So minus mu j transpose. Okay. And there I have updated all the parameters. Updated all the parameters. Okay, so if I know the bump memberships, which I start off by knowing, then I can get updates for all the parameters. But now I can update the bump memberships. So step 2, update the bump memberships. Okay, so gamma nj is going to equal, okay, so now you can think of the probability density. So the probability is the probability that xn came from bump j divided by, the total probability density. So this is the probability density that xn came from bump j divided by the sum of all the probability densities for each bump. So in other words, normalized, so that it must have come from some bump, divided by the sum over j of the probability that xn came from bump j, which is just equal to, okay, what are the chances that the data point xn came from bump j? Well, it's the weight of that bump, so wj, times the probability density, the probability to generate that data point, assuming that it came from that bump with that center and that shape, okay, which is the normal distribution function for xn, okay, given mu j sigma j, okay, divided by the sum over all j, wj, the normal distribution for xn for mu j and sigma j. Okay. So this is the probability that a data point is generated from bump j. It's the number of data points, fractionally speaking, that reside under bump j. Okay, so it's this number, and now a data point has some probability to be generated by that bump. That's what this normal density quantifies. So the probability to pick that bump for generating the data point, and then the probability to generate that data point given that bump's center and shape, okay, divided by that same quantity over all bumps, so that this thing now sums to 1 over the bumps. Okay, so now let me erase the actual. So this guy here, this normal density is what we had here. Okay, let me erase it. You can always look back in your notes or look it up. Okay, so that it's now clear what the 2 steps of the algorithm are. Given that you have bump memberships, update the bump parameters. Given that you have bump parameters, update the bump memberships, and rinse and repeat. Recycle. Repeat. Until convergence. And it typically converges very fast. Okay, so this is, now you can see the formal derivation of this as an expectation maximization algorithm. Okay. And one can show that this algorithm is guaranteed to improve the likelihood, okay, at every step. So the likelihood is always increasing, okay, but it doesn't necessarily go to the global maximum. Okay, so this is the EM algorithm for learning a Gaussian mixture model, and that's a beautiful model for density estimation. And this is the picture that corresponds to that model. Okay. So now let's go to the slides, and I'll show you this model in action. Okay, so what we're showing here is the 10-center Gaussian mixture model used to model the digits data. And you can see how beautifully, the 10 centers capture the various positions of all the, different types of, digits. Okay, and on the right are the density contours. So that contour plot where we have the intensity and the symmetry. Okay, and red means high probability and blue means very low probability. And in black, we have sort of identified the centers of the bumps, the centers of the Gaussians, and you can see how they're spread out, to capture the various digits. And it's very instructive to compare the Gaussian mixture model on the right with 10 centers and the 10 clustering. So the k-means algorithm with 10 centers. So the k-means algorithm gives a lot of information, but look at how beautifully the Gaussian mixture model, shows you, highlights the clusters and shows you the extent of each cluster. I mean, it's very similar to the k-means clustering, but the Gaussian mixture model is a soft version of clustering. Okay, it's a very powerful tool for modeling and organizing data, the Gaussian mixture model. So is clustering, by the way. So, that concludes our peek at unsupervised learning. Basically, how do you organize the data? How do you model the data? So on the one hand, k-clustering organizes the data into k clusters. The Gaussian mixture model organizes the data into k mixtures of a density, which in this case is a Gaussian, and then you can extract clusters from the density if you want. It's a soft version of clustering. Okay, so that's unsupervised learning. It's a huge field. We've just touched on it, and with that, we're checking out. See you next time.